Hello there, welcome back. If you're coming back, if you're not coming back, you're stepping right into the middle of something, and if you want to get to the beginning, there's a link in the description. This program here now contains the fix to the problem, and well, I just missed it, but it just printed out the current running time, 3:33, I think it said. I have to pause for a second when it does that so that I have a chance to maybe read it. I don't even think that was fast. It comes up every 10 seconds, so just wait a minute and I'll hit the real pause key when I see it. Where are you? Seems like a lot more than 10 seconds. Maybe it's not always. It paused there. It probably didn't have enough time. There's probably so much queued up and it never even got a chance to print itself. Let's put a breakpoint here. Then we'll see this time. 10 minutes. Okay, now I've guarded myself against the double escape by forcing myself to hit the space key in order to quit. So if I hit escape twice, it won't take me out, and there'll be a chance for the whatever remaining calls there might be to get invoked. This should terminate normally without any memory leaks. There's no, I left that access count in, okay, now for both methods. And I haven't received one yet after 10 minutes. I'm going to hit escape now. I've hit escape several times. And so you see that even though I hit escape, there were still quite a few left to print out. Now I'm going to hit space. And that's it. It exited quickly and no memory leak, and everything's cleaned up. Now, how did that work? Well, the answer lies in this thing called a synchronization object, or a Mutex object, that I'm using instead of Boolean. In fact, I could have started with another type of object called a critical section, which has this pretty much the same interface and features as Mutex, but I chose Mutex instead. Critical section is actually a simpler object, and its implementation is quite a bit simpler, at least according to the help file. It says that the mechanism it uses is a processor-specific test and set. Now, I already knew when I read this line what test and set was, almost completely, because I've been trying to figure out how a mutex is implemented. That is, how do you make that test and the setting atomic? And the only thing I could come up with is it has to be something to do with the processor. So I went looking in my manual. And again. Okay. DO means dev open. Quite a useful little tool. Unfortunately, it's a habit of killing the help file. Yeah. Now I went looking through these instructions, and I was looking for ones that said 386 plus. And the first one I saw was this byte, well, these ones, and then byte swap, which sounded almost like something that could be used for that. Then bit test, and then I saw this test and set. Okay, so I'm going to search for this. And it doesn't really give much information. Now the destination thing here can be register or memory, and the source can be, I'm not sure what immediate 8 means, or register value. Register 16, I'm not sure why it says 16, but I guess that would be like low word of AX, so AX, right? But the important thing is that the destination can be memory. Now, assuming that this is atomic, meaning that no task switching occurs between when this instruction began its operation and when it completed its operation, then that would be one way to implement a mutex. Now it turns out that this is not completely atomic. It would be on a single processor system, but if there's a multi-processor system, like most of them are nowadays, then in order to make this atomic, you need to prefix it with another instruction called lock. And what that does is that locks the CPU assert bus. Okay. Oh, sorry, the CPU bus. The CPU assert bus, well, whatever the wording they use, to avoid two processors from updating the same data location. So if there's a inside the processor. Well, in the old days, it was possible to have two processors on the same motherboard. Okay. Nowadays, you can have two processors in the same chip. So actually, you may not need this lock, because what this does is it locks up a bus. But maybe there's a little bus, an internal bus in the processor, and it certainly wouldn't hurt to prefix the lock, the test and set for the lock. Now, going back to test and set. That's exactly what we wanted. We wanted to see if something was true, and we wanted to set it up when it became true with the Boolean anyway. That's what we wanted to do, right? the idea was correct in order for the mutual exclusion. I mean, you'll notice that all I did was change the access method, but the code is essentially correct. Where did it go? BTS. So you could implement a mutex if the memory location were the Boolean thing, right? And you execute BTS. Unfortunately, I don't understand how it can be mem16. I guess a word value. I wonder if it would compile. I'm curious. Okay, I'll try that later. For now, let's have a look at Mutex. It wants to help with that. Now, amongst the many synchronization objects that are available in Windows, Mutex is but one of them. Mutex has certain special features which make it perfectly suitable for what we're trying to do. And in fact, the word Mutex derives from mutual exclusion. And the mutual exclusion that they're talking about is mutual thread exclusion. I did a little more research, by the way, before starting this video, and I found out that a thread, okay, the thread, how would we call it, object, is something that is like one of the basic units of computing, okay? Like it's something that exists at the hardware level, at the processor level. Now, a process is something that is a made-up thing by the operating system. The most basic object, the most basic task-related object in computing is a thread. Okay. Now, a process typically has one or more threads in it, and that's how you can do multiple multitasking. Right? However, when a context switch is interprocessed, right, then much more changes than simply the stack. Many other data structures need to be swapped to, or out of memory in order to switch from one task to another. You're going, in that case, you're going from one address space to another, right? Where the same pointer would have a different meaning. The same pointer number value would have a different meaning. Like all of our programs, start out at the same address. They all start at 40,000 something or other, right? Now, how could it be or 46? Okay, now how could it be possible that every single program starts at the same address? The reason is because although the numeric value is the same, the they refer to different physical memory locations. Right? The actual starting point is here, which is closer to 4100, and usually it's 410,000 is the entry point. Oh, I can go further back. Okay. No, that's still 40. Anyway, that doesn't matter. Oh, here. No. To see what the actual entry point is, we have to dump in. I think we're in debug unit mode. Entry point 411. Yes, it's usually closer to. Oh, it's because it was W main, and I was looking at a different one, I think. I don't think I managed to get to this one. Obviously, I didn't. It was all 46-ish. Okay. And the image location, the image base, is always 40,000. Okay, for every program. Obviously, every program can't be starting at the same address in memory, right? So this is like a virtual address. Okay, and it's up to the operating system to decide where to map that in physical memory. Okay. Now, why was I talking about that? Oh yeah. So I'm just wanted to mention that these thread things are something. These thread units are something to do with the hardware. It's not something that was made up by the operating system. The fact that some operating systems are said to be threaded or not multi-threaded. Some are multi-threaded, and Linux is not multi-threaded, something like that. Has nothing to do with the hardware. That has to do with whether or not they're using that particular feature of the processor. Okay, and some operating systems don't, probably for some of the reasons that we run into. It's quite difficult. Well, actually, not that difficult to prevent mutual access. All we had to do was use that Mutex thing. Now, going back to the help. Now, all of these things, when you get down to these basic functions, all of these things have something called the security attributes. And I want to talk about these security attributes structure. In fact, that's what we're aiming at. But typically we put no for that value. If you don't know any better, just put no. Okay. In the case of a Mutex object, okay, this is an invention of the operating system. This is not a processor thing. If you put no, then it says the handle cannot be inherited. Now, what does that mean? That it can't be inherited. That means that if your process spawns another process, that handle would not be valid in the spawned process. So your children, if there were children for your program, they would not be able to use it. Okay. Alright. Now, the second parameter has to do with the way the thing works. Mutex is something, it's one of those, like I said, it's one of those waitable objects. We've seen some others. It's something that you can call that wait for single object function with, that I've used several times. It should be mentioned here. Yeah, see, it doesn't even list it for some reason. Well, I would get there if I clicked on here. Okay. So all of these synchronization objects are objects which will be accepted by this function, and this is sort of a multi-purpose function, and it does different things depending on the type of handle that's passed in. In the case of a mutex, what happens is, well, point 0a, this thing returns, okay, and when it returns, it tells you why it returns. Maybe it will never return, okay, but if it does return, it tells you why it returned. And typically there are these three main return values, okay. This one in particular only applies to mutex objects, okay. No other waitable object will return this value as the reason for why the wait completed. Otherwise, since this is wait for a single object, it returns what this is the standard return, okay. Wait object underscore number, okay. In the case of one object, that number is 0. And when you get that return, that means the state of the specified object is in the signaled state, okay. Now if you were waiting on 10 objects and you got back wait object underscore 10, 0 plus 10, 9 or whatever, then that would be that the 10th object has been signaled. You see what I'm saying? This tells you which of the objects was in the signaled state. And the other possible return is if the wait timed out, and that's because you can specify a timeout value for your wait in milliseconds. Alright? Milliseconds vword value means that this in fact will wrap around after about 50 days for the same reason as our tickers. Okay. So in the case of a mutex, if this is returned, what is called ownership of the mutex is granted to the thread, the thread who was waiting, okay, and for which the wait terminated. And the mutex is set to non-signal. Now that's interesting. Now it should be normally when this quits, the state of the object is in a signal state. Okay. Now with a mutex, object, which is a special type of thing. It has an associated owner. Okay. Initially, you can set that owner to nobody. When the wait completes and nothing bad happened, so if the wait completes and nothing bad happened, then the thread that was waiting now owns the mutex. Okay, is now granted ownership of the mutex. Now it must be that the state of that object would be signaled, but actually maybe it wouldn't be signaled. That is, maybe it was signaled, right, and then it immediately became unsignaled. Because you have to remember that for mutual exclusion, if we had 10 threads waiting on the same calling wait using the same handle, right, and one of those threads is granted ownership, then one of those threads would see the object as having been signaled. But if it remained signaled, all the other threads waiting on it should also see it as signaled, and you wouldn't want that to happen. So perhaps that's the normal behavior, but I don't know how to check for that. I'm going to try to check for that. Now that's generally true, okay? No matter how many threads are waiting on the same mutex, one, and only one, will be granted ownership. And the granting of ownership occurs typically in the order in which the waits were initiated. Now what I could do is I could write a program, I hit pause, and write a very simple program and create 20 different threads and one mutex. Okay? And then have them all do something, randomly wait for a certain length of time, and then do the next thing which you have to do when you're finished using it. When you're finished when you believe that you no longer require the mutex, you must release it. Okay. And when you release it, then another thread will get a chance to do its thing, right? Now, the reason I'm having trouble with this, is it set or is it not set, and making sure to get that right, is because every time a mutex is acquired, okay, it has to be released, okay. But if I call another function that also has a wait for the same handle, for the same mutex, that wait will succeed immediately, okay. So that would seem to indicate that the object is in the signaled state, right? It won't wait. And for every time I do that, I need a corresponding release. So if I call wait successfully 10 times, I need 10 releases in order to give the mutex back to the system so that some other thread can own it. Now the question is, if the wait abandoned error is returned, okay, return value. Okay, I guess there's that possibility. if the wait abandoned, I read this somewhere, occurs, then ownership of the mutex is granted. However, we just read in the other help that although ownership was granted, the mutex is not signal. And now looking at this code here, write to a database, so blah blah blah. If wait abandoned got ownership of abandoned mutex, return false. Otherwise release. I see. So in fact, my code, what I've got here, is incorrect. If I get a wait abandoned, I definitely don't want to go and release it, right? Because its count is 0, even though I own it, right? No, but then how do I let somebody else own it? Oh, I guess I don't know. See, I don't know. That's one thing I don't know about it. Figure it out. I don't think this is going to happen anyway. This would happen in the case of a crash. When things crash, we usually quit. We don't bother trying to recover. So what I'm going to just say here, this is the result. It's going to be that. So true if the wait succeeded and I got wait object 0. And in the other case, I won't increment the number of accesses, return false. And if somebody actually used this return value, which none of them do because this is set to infinity, they could take proper precautions and make sure not to call this. In fact, well, I've got an assert here, so I turn this into a ret assert. If number of accesses is already 0, then return. But of course, this is really only here for debugging and making sure that we're getting our mutual exclusion. The error, right? If this is 0, isn't here, right? The error is with the person who called release when they were given a false return on acquire. So it would be incorrect to use this value to decide what to do here. We're just going to do exactly what we've been asked to do. We're going to release the mutex, even if that is a bad thing, because the mistake isn't here, and we log the error. Okay. Now this here is just I can get rid of that assertion now. What did I just do? I did assert. Did I assert? I did assert. Okay. Everything here has if, what's it, right? What was I searching for? If, yeah, I see. If IFF means if and only if. Let me check my time. Okay, so like I said, the person, the thread for whom the wait succeeds is the one and only thread in the entire process for which that is true, and therefore that enables us to implement a type of mutual exclusion. In this case, it was for our list, which uses the same handle. So it is a literal impossibility because of the way we've set it up for this code to be executing at the same time as this code here. So I noticed this bug before. It's supposed to be one or the other. This one also waits on the same mutex. It's a different thread. So there is no possibility that those two sections of code can be run concurrently. So that's a mutual exclusion. Now, that doesn't mean, of course, that this variable is safe. This acquire is not a property of the variable. It's a mechanism that we're using to protect a variable from multi-use. It is possible, because of some of the language features of C++, to create variables that are not accessible by multiple threads. Okay, you could create a class which in all of its member functions, right, contain one of those waits, and then a release, let's say, at the end, so that and if every single member function of the class had that property, and that was the only interface to using that class, then you wouldn't need any extra synchronization elsewhere. It would be a self-protecting entity, right? So that's something that we'd like to look into. And in fact, what I want to do, what I will do, is create a mutex type of structure, right? That one could use, perhaps something you can derive from, to simplify the construction of a protected object. Okay, so that's mutual exclusion, and as you'll notice, these warnings coming up, okay, have to do with the non-thread safety of something that I'm doing here. And what is this doing? It's constructing a static object, okay. Now, in a function. Okay, this is some function, and what could potentially happen is one thread could enter this function and start constructing that object, whatever it is, happens to be a function pointer, and then a task switch could occur, and another thread could come in here, right, and start doing the same thing, and then you have two processes halfway between assigning this variable. I don't know why I don't get this warning on here. Maybe because it's a Boolean value. Static dummy var equals false. I'm not sure why. I should get it on any kind of construction of it. Here's another static construction for which I'm not getting the warning. I think probably because there's a function call here, maybe, so that takes extra time. I don't know. Construction of local static objects. Anywhere else that I get it? No. Here. Now it's very strange that I don't get the warning. Oh, maybe I just disabled it here. Maybe that warning is disabled temporarily here. No, it should be on. And where is this one? Where is this one defined? That's in common.english. Here I've suppressed the warning. I'm not sure. But anyway, what I need to do is create a mutex for this function, a global mutex, and another one for those other functions. Okay, I have to think about that. How many of these mutexes do I need? Is one enough, or would one run me into trouble? I got to think about that. Anyway, so that's this bit. You now know a little bit about mutual exclusion objects, mutex objects, the ownership idea, and I may talk a little bit more about synchronization objects, some of the other synchronization objects. In fact, I will, because what I'm going to do is I'll just group them all the common ones together in one file, and then I'll go through how each one works, and then we'll be done with that. And then I want to move on to the other topic that I'm trying to get to, which was this idea of security. And the reason that I can make this diversion is because in using these security functions, I'm getting this warning, and I got to get rid of the warning, and instead of just magically invoking mutexes and so on. I'll let you know about what that is. Okay, see you next time.